Hi, it's me, Teacher Issa, and welcome to my channel. If you are new here, kindly hit the subscribe button and click the notification bell so whenever I upload videos, you'll get notified. Welcome to our virtual classroom, my dear students. In our class, we respect each other, we do our best, and we support one another as we learn together. Hi students! How is everyone doing? I hope you're doing well. By the way, did you send text messages to somebody today? Or have you watched your favorite TV shows? You have learned that electromagnetic wave is applied in wireless communications among others. In the succeeding discussions, you will venture into how this wave is used in sending information and messages and how wireless communication has affected people's daily affairs. So, what do you mean by wireless communication? And how this wireless communication become possible? In the previous lesson, you were able to describe the different regions of electromagnetic waves, such as its frequency and wavelength. The different regions of electromagnetic waves are radio waves, microwaves, infrared, visible light, UV rays, X-rays, and gamma rays. So in this topic, you will cite examples of practical applications of the different regions of electromagnetic waves. So let's get started. The first one is radio and microwaves in wireless communications. So what are the applications of these waves or electromagnetic waves? So we have here the radio communication. Today, conversations, data, and even music can be transmitted through air over millions of kilometers because of radio waves. Wireless communication has become possible through transmission and reception of these radio waves. Remember, radio waves can be transmitted through empty space. As you can remember, radio waves have the longest wavelength in the electromagnetic spectrum, and they are produced by making electrons vibrate in an antenna. Medium and high-frequency waves are used for broadcasting by local radio stations. In a radio station, sound is converted by a microphone into patterns of electric current variations, and this is called audio frequency signals. And high-frequency radio waves called radio frequency or RF carriers can be modulated to match the electronic signal. In amplitude modulation or AM, the amplitude of the radio waves or RF carrier changes to match that of the audio frequency or AF signal. This is used in standard broadcasting because it can be sent over long distances. Very high frequency waves provide a higher quality broadcasting including stereo sound. In this process, instead of the amplitude of the RF carrier, it is the frequency of the waves that changes to match that of the signal. This is called frequency modulation or FM. When the radio wave is received by the antenna of a radio or television, the pattern is converted back to its original form. The sound portions of most television broadcasts are carried as AM waves, while the picture portions are carried as FM waves. They are used to transmit sound and picture information over long distances. Radio waves have a very wide range of wavelengths. The whole region of the radio waves is divided into smaller regions of wave bands, and each wave band is allocated by law to a specific radio service. Low-frequency waves are suitable for communication over great distance, but the curvature of the Earth limits the range to about 80 kilometers. To extend the range, a repeater is used. So, what is repeater? The repeater receives the signal and retransmits it to the receiving station. High-frequency waves can be reflected by the ionosphere, and this enables the waves to be transmitted over great distances. Did you know? Frequency is an important characteristic of radio wave. AM broadcast frequency is about 1 million cycles per second or hertz. For example, when you tune in to your favorite AM radio station at 630 on the dial, the radio is tuning in or tuning to the radio wave with a frequency of 630,000 cycles per second. On the other hand, FM radio operates on 100 million cycles per second. So when you turn to 101.1 FM, your radio is tuning to 101 or 101,100,000 cycles per second frequency. Next is the satellite communication. We know for a fact that radio waves travel in straight line. Why then are we able to receive messages or information from other parts of the world? First, let's take a short review of some facts we learned in Earth science. One layer of the atmosphere is composed of ionized gases, and this layer is called ionosphere. Therefore, communication satellites are used to reflect these waves back to Earth, which are then captured by the receiving antennas. Communication satellites travel around the Earth at an altitude of 35,000 km above the equator. They move at a speed of 11,300 km per hour and revolve around the Earth every 24 hours. The same rate as the rotation of the Earth. This makes them appear stationary when seen on Earth. Antennae are mounted to point in fixed directions towards these satellites. Microwaves can penetrate the atmosphere of the Earth. This is the reason why they are used for satellite communications. Microwave signals retransmitted by an antenna to a satellite which amplifies and retransmits the signal to an antenna in other parts of the world. This is how we communicate with the rest of the world. Most communication satellites are used to send and receive radio signals for telephone services, while the rest are for television broadcasting, scientific research, and weather forecast. Microwaves have short wavelengths and are reflected by small objects. This property is used in radars. Radar is an acronym of radio detection and ranging. A radar system consists of an antenna, transmitter, and a receiver. The antenna whirls around continuously to scan the surrounding area. The transmitter sends out a narrow beam of microwaves in short pulses. A distant object reflects some of this signal back to the receiver. The direction to which the signal was received gives the direction of the object. The distance of the object can be calculated from the time lag between the transmitted pulse and the reflected pulse. Again, radar or radio detection and ranging. This is used to locate, track, recognize, or detect object within a range. It emits microwaves until it reaches the target, and echoes will be produced from the target and will bounce back to the radar antenna. It is commonly used in national defense by tracking aircrafts and ships from other countries that may trespass and cause threat. But did you know that it is also used by our vehicles? Radar is also used to determine the velocity of automotive vehicles. So if you are familiar with the Dragon Balls, you now understand how Son Goku and friends had traced all of them. Let's proceed to terrestrial communication. Do you notice that a lot of people now resort to cable TV for news, entertainment, and educational programs? CATV, or cable TV is now used because of its wide range of channels and clearer sound and picture. Moreover, some cable companies provide internet access to users. How does this amazing CATV work? Microwaves are used to transmit television news coverage from mobile broadcast vehicles back to the station. The news crew can also set up a small antenna to send signals to a communication satellite. This is how news are broadcasted and watched live around the world. A cell phone is a radio transmitter and receiver that uses microwaves. It is today's answer to the emerging demand for mobile communication. Cellular phones depend on overlapping network of cells or areas of land several kilometers in diameter. Each cell has its tower that receives and sends microwave signals. So this is the other application of microwaves. Microwave oven is used to cook or heat food. How? When you turn on the microwave and started to set it, the water molecules of the food inside start to vibrate through microwaves, causing the production of intermolecular friction between the molecules of the food. As a result, heat is produced that will make the food to be cooked. Our next topic is the application of invisible heat, visible light, and ultraviolet light. In this particular topic, you will be able to learn that most of the EM waves are detectable and can be seen in our naked eyes. So in the previous topic, you have learned about radio waves and microwaves. Both are used in wireless communication. Wireless communication has become possible through transmission and reception of these radio waves. People around the world are now able to communicate with one another through innovations in technology. Cell phones are very familiar to youngsters like you. You can talk to your friend in another country using this small gadget and you feel like he or she is just around the corner. Cell phones, along with other telecommunication devices, have made distance immaterial. Wireless communication has made the world smaller. In your own idea, what does a wireless communication mean? So let us discuss the invisible heat. Infrared waves are in the lower middle range of frequencies in the electromagnetic spectrum. Infrared radiation lies beyond the red end of the visible light. The size of infrared waves ranges from a few millimeters down to a microscopic lens. The longer wavelength infrared waves produce heat and include radiation emitted by fire, the sun, and other heat-producing objects. Shorter wavelength infrared rays do not produce much heat and are used in remote controls and imaging technologies. The amount and wavelength of radiation depend on temperature. So, below 500 degrees Celsius, an object emits only infrared radiation. Above 500 degrees Celsius, an object glows and emits both infrared and visible light. The difference in color determine the differences in temperature. For examples, shades of blue and green indicate regions of colder temperature, and red and yellow indicate warmer temperature. The human eye is not sensitive to the infrared light used by television remote controls. To send a signal to a television, remote controls often use a diode that emits light. Some digital cameras have filters to block near-infrared light, but most can detect it. It shows up on the screen as if it were visible light. When you press a button on the remote control, the camera may show a pulsing light emitted by the remote. The following are some useful applications of infrared radiation. Number 1. Infrared photographs taken from a satellite with special films provide useful details of the vegetation on the Earth's surface. Number 2. Infrared scanners are used to show the temperature variation of the body. This can be used for medical diagnosis. Infrared remote controls are used in TVs, video, cassette recorders, and other electronic appliances. Number 4. Some autofocus cameras have transmitters that send out infrared pulses. The pulses are reflected by the object to be photographed back to the camera. The distance of the object is calculated by the time lag between the sending and receiving of pulses. The lens is then driven by a built-in motor to adjust to get the correct focus of the object. And the last one is a night vision goggle. Next is the applications of visible light. When white light passes through a prism, it is separated into its constituent colors: the red, orange, yellow, green, blue, indigo, and violet. These colors do not distinctly separate, but they continuously change from red to violet. Red color has the longest wavelength from among these colors, and violet has the shortest. Our eyes are sensitive to electromagnetic waves of wavelengths that ranges from 4 times 10 raised to negative 7 meter to 7 times 10 raised to negative 7 meters. This is the range of wavelengths of white light. Thus, the spectrum of white light is therefore called the visible spectrum. Visible light is essential for photosynthesis. Photosynthesis is the process by which green plant makes food. Forms of energy taken from the sun used by the plants and microorganisms million years ago are locked up in coal and oil used as energy resources today. Next is the production of light. There are several ways in which a luminous object can be made to give off energy in the form of light. A luminous object can produce incandescent light, fluorescent light, and neon light. The first one is incandescent light. This is a form of light produced by heat. Ordinary light bulbs in your home are incandescent. They produce light when electricity is applied to them. Inside the glass bulb of a light bulb is a thin wire filament made of metal tungsten. Tungsten can be heated to over 2000 degrees Celsius without melting. Next is fluorescent light. This is cooler and uses much less energy than incandescent light. Instead of being used up to build up heat, electrons in fluorescent lights are used to bombard molecules of gas kept at low pressure in a tube. The color that a fluorescent bulb produces depends on the phosphors used. And the last one is the neon light. Neon light can be seen in thin glass tubes of brightly colored lights. It is a cool light similar to fluorescent light. When electrons pass through the glass tubes filled with certain gases, light is produced. The most common type of gas used is neon gas, which produced bright red. If other gases are added, however, different colors are produced. Next is the application of ultraviolet radiation, the heat energy. Ultraviolet radiation lies just beyond the violet end of the visible spectrum. Ultraviolet waves have shorter wavelengths than the visible light and carry more energy. Ultraviolet rays are best known to come from the sun, and many are afraid of it. But did you know that it is needed by our skin? It helps our body to produce vitamin D, which is essential in our body's calcium absorption. But too much exposure to UV rays will make our skin to accelerate in aging, or worse, it may lead to skin cancer. Aside from the sun, there are artificial sources of UV light. We have UV lamps, which are used in checking signature on passbook, though this one can determine fake banknotes as well as fake money bills. The signature is marked on the passbook with fluorescent ink. It becomes visible when viewed under an ultraviolet lamp. Ultraviolet radiation is also used in sterilizing water from drinking fountains. It is also used in our water filters being attached on faucets. Some washing powder also contains fluorescent chemicals which glow in sunlight. This makes your shirt look whiter than white in daylight. In Japan, UV rays are also used to disinfect their toilets. Our last topic for today is the application of penetrating radiation and nuclear energy. In this particular topic, you will be able to learn that in the electromagnetic spectrum, the longer the wavelength in the EM waves, the lower its frequency. Thus, the lesser the amount of energy it has. In the previous topic, you understand the application of the three types of EM waves: the infrared, visible lights, and ultraviolet rays. The amount of infrared given off by the object depends on the temperature of the object. The use of infrared scanner in medical diagnosis show the temperature variation of the body. Visible light is the only EM wave that our eyes can see, and life on Earth could not exist without visible light. And lastly, ultraviolet rays and UV lamps are used by banks to check the signature on a passbook and also used to identify fake banknotes. Radiation is the transmission of energy in the form of waves or particles through space or through a material medium. It may take such forms as light, or tiny particles much too small to see. Visible light, the ultraviolet light we receive from the sun, and transmission signals for TV and radio communications are all forms of radiation that are common in our daily lives. These are all generally referred to as non-ionizing radiation, though at least some ultraviolet radiation is considered to be ionizing. Radiation particularly associated with nuclear medicine and the use of nuclear energy along with X-rays is ionizing radiation, which means that the radiation has sufficient energy to interact with matter, especially the human body, and produce ions. Let us discuss the applications of X-ray or the penetrating radiation. X-rays come just after the ultraviolet rays. They are of shorter wavelength but carries higher energy than the UV rays. X-rays are produced using an X-ray tube. They are emitted when fast-moving electrons hit a metal target. X-rays were discovered by Wilhelm Conrad Roentgen in 1895. Long-wavelength X-rays can penetrate the flesh but not the bones. They are used in X-ray photography to help doctors look inside the body. They are useful in diagnosing bone fractures and tumors. Short-wavelength X-rays can penetrate even through metals. They are used in industry to inspect welded joints for faults. All X-rays are dangerous because they can damage healthy living cells of the body. This is the reason why frequent exposure to X-rays should be avoided. Too much exposure to X-rays can damage body tissues and can cause cancer. The last one is the applications of gamma rays or nuclear energy. Gamma rays lie at the other end of the electromagnetic spectrum. They are shortest in wavelength and highest in frequency. Gamma rays are emitted by only the most energetic cosmic objects such as pulsars, neutron stars, supernova, and black holes. Terrestrial sources include lightning, nuclear explosions, and radioactive decay. Gamma wave wavelengths are measured on the subatomic level and can actually pass through the empty space within an atom. Gamma rays can destroy living cells. Fortunately, the Earth's atmosphere absorbs any gamma rays that reach the planet. Gamma rays carry the highest amount of energy, thus, they are more dangerous. They can also be blocked with lead and thick concrete. Gamma rays are very strong that they can kill living cells. Gamma rays are used to treat cancer through the process called radiotherapy. They are also used for sterilization of drinking water.
shake it, baby.